Well, team, are you ready to do Born-Haber diagrams? One of my absolute favorite things in all of chemistry to do. Like I said, kind of weird, but that's why I'm a chemistry professor. I love dimensional analysis. I love Born-Haber diagrams. These things are awesome. So these are great little shortcuts. So that last video on lattice energy in the Born-Haber cycle, I went through Hess's law, and we did path 1 equals path 2, and did all the equations and cast it all. I got a little throat in my throat. That takes forever. So we like shortcuts. There's not many shortcuts in chemistry, but we like them when they're there. The Born-Haber diagram you will learn to love because it's a nice, beautiful shortcut to that Born-Haber cycle. All right, we don't have to write so much. We're just going to go boop, 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 bang, 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 done. Yes. All right. So we'll do it for silver oxide, and if we have time, we'll do it for a whole new compound and go through. Let's put the numbers to silver oxide this time. We'll look up, ionization energy values and show you where to find those and put them down. And then we'll do another one, but we'll just set up the equation and not throw the numbers into it. And I'll show you. You can whip these up pretty fast. So you can test them with your friend. You can say, hey, do, iron 3 chloride. And have them go at it. Do, rubidium bromide or, tungsten 5 phosphide. I don't even know if that's a compound, but you can have some fun with it and you can test each other with it. All right, so these are diagrams. I kind of showed you that in the beginning where we went path 2, the chutes and ladders things, path 1, path 2, and they'll equal each other. We're going to do that where we're going to put the details in. So, and it sums up the Born-Haber cycle that we did in Hess's law for ionic solids. Any ionic solid you want, right? So you just say, I want 1 mole of this ionic solid. Make sure you get the correct formula for that, chemical formula. All right, and so again, Born-Haber diagram is going to act as a shortcut to the Born-Haber cycle when we're solving for lattice energy values, or really any value that appears in the Born-Haber cycle. So we could solve for bonding energies if we knew everything else. We could solve for standard heats of formation if we knew everything else. First, second, third ionization energies, first, second, third electron affinities, molar heats of sublimation, molar heats of vaporization, any variable that appears in there, as long as we know all of the other variables except for that one, we can solve for that one. But the majority of the time, we're going to be solving for lattice energy. Let's do it for silver oxide. Yay, I'm so excited. All right, here's the basic premise for doing a Born-Haber diagram, okay? Identify the correct chemical formula for the solid, in this case, silver oxide. Silver's a +1 cation, oxide's a -2 anion. We need 2 silver ions, cations for every 1 oxide anion. Draw that 1 mole. By definition, we're forming 1 mole of it exactly. Put that on the very bottom and just put a line across, all right? And what we're going to do, the starting point is the elements in their standard states. We're going to start both pathways. We're going to have one person run this direction and one person run that direction. Okay, obviously this one's going to take a lot longer. So start with the elements in their standard states. This is the reaction for the standard heats of formation. Okay, so if we're forming 1 mole of silver oxide, we need those 2 moles of silver in the solid phase. That's the standard state. Half a mole of diatomic oxygen in standard state. Half times 2 gives you 1. Right? That's your starting point. Path 1, boom. Path 2, we got to get to the ions in the gas phase and then come down using the lattice energy. So I'll usually put the elements in their standard states off to the left, maybe about a third, fourth of the way up. And then in the upper right-hand corner, I'll put the ions in their gas phase. So 2 moles of silver cations in the +1 charge, gas phase. 1 mole of the oxide ion and -2 in the gas phase. Boom, that would be your lattice energy from here to here. But path 2 starts here and goes all the way around through the bond energies and the ionization energies and electron affinities. Of course, Hess's law says path 1 in green must equal path 2 in blue. This is the basic premise for every solid. Whatever the solid is, just make sure the coefficients are correct. Okay? Now, one thing to remember, it's like chutes and ladders. Ladders go down, chutes go down, ladders go up. In this, it's going to be, is it exothermic or endothermic? So remember this concept right here. If it is an exothermic process, it's downhill, right? So lattice energy is an exothermic process. Standard heats of formation are typically going to, if you're forming this, it's going to be an exothermic process, depending on what it is, right? So exothermic processes so they point down. So all exothermic processes will point down, dropping in energy, right? The system is losing energy. Any endothermic process is like climbing a ladder, right? So exothermic, releasing energy, slide down the slide, yay. Exothermic, man, I gotta climb the ladder, it takes energy. So anything that's endothermic, bond energies, ionization energies, right? Those kinds of things, sublimation energies, those are endothermic processes. They're gonna go up the ladder, up the rungs of the ladder. Okay, so exothermic process points down. An endothermic process points up. So sometimes you can just qualitatively think about that, but you can just look on the tables, right? Especially electron affinity. So bond energies are all positive, so they're always going to go up, right? If you look at standard heats of formation, right? Yeah, most are negative, but some are positive. In this case, they're all going to be negative for favorable ionic solids. Ionization energies are all positive, so they're all going to point up. Removing an electron requires energy. Electron affinities can be negative or positive, right? Look at oxygen. The first one's negative, second one's positive. So it's going to go down and then up. Down a little bit and then up a lot. So negative 100 is about here to here, and the positive 700 is here. So try to reflect the size of the delta H value, right? So if 100 is this high, 200 is that high, 300 is that high. So try to reflect that based on how much, I don't have a lot of space on here, right? But do the best you can. So there's your rules for the game. Endothermic points up, exothermic points down. Try to adjust the size of the arrows based on the size of the delta H, but not critical, especially if you're out of space. And the little spaces I give you on the exam. And path 1 equals path 2. So let's do it for silver oxide. Let me erase this mess, and then we'll get from here to there, and then come down with the lattice energy. So get the notes out from the last video. This will help you follow it. All right, let's walk through it. Just think about it, right? And review any videos you need from last semester if you're stuck on electron affinities, ionization energy, standard heats of formation, Hess's law. Make sure you review, right? In between, your full-time job, significant others, other classes you're taking, social things with your friends, right? You can slip it in the crack, right? All right, let's look at path 1. We know that is the standard heat of formation, right? Boop. Let's look it up on a table. We're good to go. Now let's do path 2. Woo! We got to get to the ions in the gas phase from the elements in their standard states, and then drop down with the lattice energy. Sometimes I don't write those up there because sometimes it just doesn't quite work out, and I got to erase it and move it. But I just want to give you the idea. We're starting here, going to 1 mole of the solid in one step in path 1, and then we're going from here, then getting the ions in the gas phase, and then dropping to the 1 mole of the solid using the lattice energy. Here we go. And I like to use these little lines to underline what the reactants are, but I'm not going to draw what the products are. Okay, remember, we got to get, step 1, we got to get anything that's not a gas into the gas phase. So we need to go up to, let me erase that. So I got to get from the solid silver to silver in the gas phase. Boop. See that? So I'm going to be going up. Let's do this in blue, but path 2. And that is an endothermic process. That's the bond. That is the molar heat of sublimation times 2. Right? So I'm just doing the Born-Haber cycle that we did on the last video, but I'm just summarizing it in a Born-Haber diagram. So boop, now I've got my metal and non-metal both in the gas phase. Step 1 done. Bam! Step 2, let's get my metal into the cation. So I need to go from silver neutral to silver +1. Ionization energies are always positive. I don't even know if I have silver on here. There it is. 731.2, is that right? Yep, woo, that's going to be a lot of energy. So that's going to pop up. I don't have a table of the sublimation energy, so we'll have to look that one up. Those aren't as common. So we've got, and that's going to be probably quite a bit bigger. So let's go to 2 Ag plus gas plus 1/2 O2. I haven't touched the oxygen yet, right? And again, it's hard. I can't really draw it to scale. Really, this should be like way up here, but then I don't have room for the bond energy. So because of the limited size of my board, I can't really draw these delta H values to scale. It's unfortunate, but if you got a whole page when you're practicing, just take a whole piece of paper and you can try to draw them to scales. I'm not going to grade you whether they're scale or not, so the size of the gaps, but I will grade whether they go up or down. Endothermic must go up, exothermic must come down. So here, from here to here, we're ionizing, so that'll be the first ionization energy of silver times 2. Which is a positive value. We can see that. But you should know that, but you can look it up on the table, right? Removing electrons requires energy. All right, so that's step 2. We are now done. See, 2 Ag plus gas, 2 Ag plus gas. We're done with the metal. Now let's take the nonmetal. That's O sub 2. That's monatomic. This is diatomic. We need to break that diatomic element up. Breaking bonds is endothermic. That's pointing up, right? So let's go to the 2 Ag plus gas, and then we are going to break that apart to get 1/2 times 2 is just 1 oxygen atom in the gas phase. That requires energy, and that is the bond energy of oxygen. Whoops. So that'll be the bond energy of oxygen times 1/2. Don't forget those coefficients, right? And we're just going to add all these together. Some people go delta H1, delta H2, delta H3. I like to do specifics. All right, so that was step 3. Now step 4, we need to convert that nonmetal into the anion, which is in 2 steps. It's a -1, -2. So what we're going to do is we're going to extend this over a little bit. And this is going to be exothermic. So if you look at the first electron affinity of oxygen, it's negative 141. That's typical for nonmetals. The first ionization energy is almost always negative, and the second is always positive. So we're going to go down and then up. Okay? So let's drop down to the 2 Ag plus. We haven't done anything of that. And then we're going to add an electron to the O minus. So I'm going to move that over a little bit. And then I will draw this pointing down. And that is Ea, the first electron affinity of oxygen, times 1. I always make sure I times it. Even if it's a 1, I'm always going to times it by something because it forces me to go, oh, because if you don't do that, you might forget the 2 or the half, right? So I'll go, that's the value times what coefficient? 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 Most students screw up the coefficients. I've been doing this for well over 2 decades, right? So now we need to get from the O minus to the O2 minus, and that is the second electron affinity of oxygen, which is positive 744. So really, if I'd done this right, this needs to be like way up here. Whoop, I'm way off the table, right? So this should be, if that's 100 something, and this is 700 something, this should point up 7 times higher. It should go way up towards my ceiling. But I've run out of space, okay? So what I'm going to do is just go up from here. You know what I'm going to do? I'm going to move this over. That's why I usually don't draw it. It never ends up in the place you want it to be. So let's dot this over. And then we're going to go up with the second electron affinity times 1. And we're going to add another electron. So we're going to get 2 moles of the silver 1 ion in the gas phase plus 1 mole of the oxygen with the oxide ion with a -2 charge. See that? And Ea2 is a lot bigger than Ea1. If this is Ea1, Ea2 should be like this. So that's step 4. These two combined are step 4. And now I've got the cation and anion in the gas phase with the correct coefficients. And I can go wee down the big chute and chutes and ladders, which makes you lose the game because you're about to win and you go all the way down. And this would be my lattice energy. So everything in blue, that plus that plus that plus that plus that plus that, should equal everything in red, that. So that's path 1. And then this is path 2. And the overriding fundamentals of this says, path 1, thank you, Hess's law, path 1 equals path 2. That's a lot easier than doing the Born-Haber cycle where you have to draw every single equation and add them all together. Right? We can do this for any solid. It doesn't matter. You might have more steps or less steps. It really doesn't matter. So let's put this all together and put some numbers to it. So that equals that plus that plus that plus that plus that plus that. Get out your electron affinity, ionization energy tables, thermodynamic tables, probably in the index of your textbook. Bond energies. What else do we need? Sublimation energies. I don't have a table of that, so we're probably going to have to look that one up in the Handbook of Chemistry and Physics or Lange's Handbook or something like that. You're probably just going to Google it, but make sure you go to a trustworthy site, okay? Not just some random blog for some 15-year-old, in some obscure state somewhere that's 1,000 miles away from you. All right, let's erase this and do that equals that plus that plus that plus that plus that plus that. Let's do it. All right, did you get this so far? We did this on the last video. We got the exact same equation from the Born-Haber cycle. We just did it this time with the Born-Haber diagram, which is a lot faster and kind of easier to see. It's not so cluttered. So remember, path 1 equals path 2. Path 1 was the standard heat of formation. Path 2 was the sublimation of the silver, ionization of the silver, breaking the OO bond, adding one electron, adding a second electron, and then combining the gas phase cations and anions to form the solid. So that should equal that. And normally, in this case, let's solve for the lattice energy, which is probably 90% of the time what you're going to do. But again, I can have you solve for any one of these variables as long as I give you all the other ones. So if I want the lattice energy, I need to take all these other ones and subtract them to the other side. So it would be the standard heat of formation minus that, minus that, minus that, minus that, minus that, and you've got the lattice energy. So what I want you to do is grab your textbook or something, preferably your textbook, or if you're in my class, you've printed out these. I want you to look up these values. So look up now on my table that I have on my website, I just have one page. So I don't have silver compounds on here, so silver's not on it. So you have to look that up in appendix. I think it's appendix D in our textbook, whatever the appendix is in your textbook. Find your thermodynamic tables and find the standard heat of formation for silver oxide. So find that for me. And then sublimation. See if you can find that in your textbook. If not, go ahead and Google it. I'm okay with that. You can't do that on an exam. So I would give you that on an exam, right? But on an exam, I would give you this table and make you find it. Or maybe I'll give you a table of sublimation values, but typically I'll just give that one to you because sublimation is not so common. Ionization energy. So look up in your textbook a table of ionization energy values. Right, so you can find that for silver. Bond energy, find your table for bond energies or use mine. Electron affinity values, find your electron affinity values for oxygen. Boop, boop, you're good to go. So what I want you to do is, I'm going to pause this and give you a minute here. Plug in the values for all of those variables and then track your insert. We're doing subtractions right now. The 2's and stuff are exact numbers, so we're going to be limited by largest absolute uncertainty or fewest decimal places. So just see which one of these has the fewest decimal places, and you're going to be limited to that with your lattice energy. Go for it. And then I'll take a minute to write those values up because I don't know that off the top of my head. I'm going to have to go find that one. Did you have fun trying to find all these values? Oh, it takes a while, doesn't it? So like I said, on exams, you want to be familiar with these tables, and then I would provide you molar heats of sublimation. That was the hardest part for me. It wasn't in the textbook. I was looking around. I don't have a Handbook of Chemistry and Physics with me at home, so I had to fart around on the on the internet. I hate doing that on the internet, and I found a whole bunch of different values. So anyway, standard heat of formation, if you look in the back of your textbook, I found negative 31.05 kilojoules per mole for the standard heat of formation for silver oxide, Ag2O. For molar heat of sublimation, I found several different values, right, giving different degrees of uncertainty at different temperatures, yada, yada, yada. I found values ranging from 266 all the way up to 324 kilojoules per mole. Well, that's pretty vague, okay? So I would give you this on an exam. So I ended up using kind of the middle one, about 285 kilojoules per mole. So your number might be a little different than mine based on the value you had there. I would provide for that, okay? So again, I'll give you that on an exam. So that was the molar heat of sublimation. First ionization energy of silver. I got 731.2 right there, times 2, of course. Bond energy of diatomic. Remember, O2 is diatomic, so you got to use the 498, not the 145. It's the double bond. So 498, and then you got to times that by a half. First electron affinity we looked at for oxygen was negative 141.0 kilojoules per mole. The second was positive 744. Watch out for the negative sign there. It's just subtracting the negative. That's the math just drives people crazy. Most people set it up right and then calculate it incorrectly. 2 decimals, ones place, 1 decimal. So it looks like we're limited to the ones place. That's the largest absolute uncertainty. So when I added that all together, I got negative 2,915.45, which rounded down to negative 2,915 kilojoules per mole. That's a really big negative exothermic things for taking metal cations and nonmetal ions in the gas phase and putting them together. All right. Now for these coefficients, you can just leave them like that, or you could go 2 moles, and then the moles cancel out, and you'll end up just getting kilojoules. But by definition, you're forming 1 mole of silver oxide, so you could go kilojoules or kilojoules per mole. Normally, it's going to be in kilojoules per mole, so I just leave the moles off there. I'm okay either way on that one. So if we've got time on a quiz or something, I may have you put all the numbers in here, definitely for homeworks and labs and things like that. On an exam, we may not have a lot of time to do this, so I might just have you set up the equation, or I'll just provide you all the values so you don't have to dork around with all the tables, right? It all depends on time limitations. Let's do one more. So I'll pick one out, and then I'm going to let you attempt it, and then see if you match what I've got. You ready for a doozer? So here's one, probably a little harder than I'd give on a quiz or an exam, but this would be fair game for maybe practicing on a homework or in a lab, or if you come to office hours. And I've had students come to office hours say, just give me a solid. I'd be like, oh, do this one, do this one. They, blah, blah. After 3 or 4, they're like, whoop, 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 piece of cake. Hardest part's just looking up the dumb values. So let's take lanthanide 3-bromide. Never seen it in my life, but hey, we're doing theory stuff, so we can do any compound we want, whether it actually exists or not. So draw the Born-Haber diagram for lanthanide 3-bromide solid. All right, and I want you to do that. So start with the, you got to get the formula right, get it on the bottom. And then once you've done that, set up the equation that relates path 1 to path 2. And I'm going to have you isolate, not for the lattice energy this time. How about the enthalpy of sublimation? We had issues with that for the silver, didn't we? So first and foremost, you need the equation for that solid. So lanthanum's plus 3, bromide's a minus 1, right? So lanthanum plus 3, bromide minus 1. Back to intro chemistry. This is your lanthanum bromide. So you're going to start with that on the very bottom. Get a whole piece of paper for me and put that on the very bottom with a big line. And then get the elements in their standard states with the proper coefficients. Get the ions in the gas phase with their proper coefficients. Do path 1, path 2, and make them equal to each other and follow the 5 steps. Do it, and let's see if we match. You ready? I'll do this one with you. Let's do it live. I'm just going to do it off the top of my head. If I make a mistake, let me know. So we need the elements in their standard states. That's our starting point, right? So lanthanum's monatomic. It's a metal, so we're going to have lanthanum solid. We need 1 mole, so we just have a 1 there. Bromine's one of the magnificent 7, right? So that's diatomic. And bromine's one of the infamous liquids. So to get 3, 2 times what is 3? So that would be 3 halves. Is that correct? So now we have path 1. And that will be the standard heat of formation. That's the equation for the standard. If you put an arrow there, that'd be the standard heat of formation equation, right? So now for path 2, we got to get from the elements in their standard states all the way to the cation and anion in the gas phase and boop, drop down for the lattice energy. Now lanthanum's a plus 3, so we got to go plus 1, plus 2. So it's going to take a while. But let's focus. Step 1, get the elements into the gas phase. Well, that's a solid, that's a liquid, so we're going to need to sublime the lanthanum and vaporize or boil, in this case, the bromine, get it from the liquid to the gas, so molar heat of vaporization. Let's do the metal first. So we're going to get lanthanum into the gas phase, plus 3/2 bromine liquid. Well, that requires energy, right? So that's going to go up. And that'll be the molar heat of sublimation for lanthanum. Now let's get the bromine into the vapor phase. So we're going to have lanthanum in the gas phase plus 3/2 bromine in the vapor state or gas phase. That requires energy, so that goes up. And that will be delta H vap. And this will be times 3/2. This will be times 1, right? For 1 for the lanthanum, 3/2 for the bromine. So far, step 1's good. Step 2, let's get that lanthanum from neutral to +3. So we got to do it in 3 steps. Remove 1 electron, then 2, then 3. So let's go to lanthanum +1 in the gas phase. Told you this one's going to be a doozer. We're not doing anything with the bromine right now. So that goes up, and that'll be the first ionization energy of lanthanum times 1. I don't know if I'm going to have enough space. I'm going to get squishy here. Let's go to lanthanum +2 in the gas phase, plus 3/2 bromine gas. Getting squishy. Right? You got a whole page, I don't. And that'll be the second ionization of lanthanum times 1. You can zoom in on the computer, right? Let's add the third one to get the lanthanum +3 plus 3/2 moles of bromine gas. Squishy! Squishy! So from there to there will be the third ionization energy. Whew, those +3, man. Imagine if we did it like a +5 or something. So get the lanthanum into the gas, get the bromine into a gas. First, so add and remove 1 electron, 2 electrons, 3 electrons. Now we got lanthanum in the +3 state. Okay, so we've done step 2. Step 3, we need to bust that bromine in half, don't we? We need bromine atoms. So we need the bond energy of that. So this is going to go up 1 more. Oh man, that's going to be, I'm going to squish it over to the right-hand side. So this should go up. Let me do a little blue thing here. I'm out of room, my friends. So that'll be lanthanum +3. And then 3/2 times 2 would give me 3 bromine atoms in the gas phase. And that will be the bond energy times 3/2. So I apologize, it didn't fit on my board. I got a little too excited. So that should go up, right? So we got lanthanum in the gas phase +3, and we got 3 bromine atoms. Now step 4, let's add electrons. Now bromine goes to a -1, so we only need the first electron affinity of bromine. And that is, and that's always going to be exothermic. So you can look on the table, that's going to drop down. I was so close, but I didn't think I could squish it up in there. So this will give us the lanthanum +3 in the gas phase, plus the 3 moles of bromine ions in the gas phase. And that's the first electron affinity of bromine, right? So we're going to take the electron affinity, the first electron affinity times 3. And now we've got the elements. We got 1 mole of lanthanum +3 in the gas phase, 3 moles of the -1 bromide ion in the gas phase. Everything matches up. Boom! Take that last chute all the way down. There's your lattice energy, right? So sublime the lanthanum, vaporize the bromine, remove 3 electrons each in turn, because I1, I2, and I3 are all different values. Split the bromine in half, add an electron to each bromine, so we got 3 moles of that, and pop! There's your Born-Haber diagram. Not too bad. So let's set up the equation. Path 1 equals path 2. So that will equal that plus 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 that. And let's isolate for that. I'm going to erase this. You do it on the next board for me. Let's see if you got this, right? So path 1 is always the standard heat of formation. Always. This is the one step. Path 2, get to the ions in the gas phase and use the lattice energy. So it's the molar heat of sublimation of lanthanum times 1 plus the molar heat of vaporization of the bromine times 3/2, right? Don't forget the coefficients. Plus the first ionization energy of lanthanum times 1 plus the second ionization energy of lanthanum, blah, 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 times 1, plus the third ionization of lanthanum times 1, those darn plus 3s, plus the bond energy of the diatomic bromine times 3/2, that Br, single bond Br, look it up, plus the first electron affinity of bromine to get to the -1 charge, times 3 because you have 3 moles, plus the lattice energy. And we are isolating for, in this case, last example, we isolated the lattice energy, which is the most common. But in this case, let's say we knew the lattice energy. I gave that to you. I gave you that, all the ionization energy tables, bond energies, this. I gave you everything except for the molar heat of sublimation of lanthanum. Oh, well, if we want that, just subtract everything else to the other side. So that'll be the standard heat of formation, minus 3/2 times the molar heat of vaporization of bromine, minus the first, minus the second, minus the third ionization energies of lanthanum, all times 1, minus 3/2 times the bond energy of Br2, minus 3 times the first electron affinity of bromine, minus the lattice energy. You'll get your molar heat of sublimation. We're not going to do numbers to it. Whew. Practice it, practice it. You're going to get so fast at Born-Haber diagrams, you might get a 10, 15-point problem. 2 or 3 minutes, you're good to go, right? Unless you have to add all the numbers, that takes another 5 minutes. We got this. Born-Haber diagrams rock!